Corrado, are we waiting for a learn Afghan? Try to speak.
I send a mail at Learn Afghan.
Maybe they have issues. You know that sometimes they do. If you want, we can start, Corrado, because otherwise I'm afraid that Mr. Merlo won't have enough time.
You can start.
Yeah, no problem for me. I can fit whatever time I have. So
okay. And how long do you expect your presentation more or less to last? You can adjust.
Depending on the question and answer, because it's a quite an interesting domain. So if we go on the question and answer, we can stay forever. So
okay.
I will tune the presentation according to the time. So if you tell me we have to finish at 1.
Yes, because our students are leaving school at 10 minutes past 1.
Okay,
that's
excellent.
Say 1 o'clock. Okay. Corrado, do you think we can start?
Okay, you can start. I send a mail at Learn Afghan.
If they can join us, they will do it during the presentation.
Okay.
Yeah. No,
okay.
No problem. So, hello everybody. So first of all, thank you very much for this opportunity. It's very important for us, for my company to give this kind of seminars, presentation, and dissemination toward school, because we like to inspire, engage for the future. So I hope to gain some CV for the next application in the next years.
Thank you, Mr. And we are really honored to host your presentation and your company.
Thank you very much. So first of all, a bit of presentation of myself. I'm Andrea Merlo. I'm the responsible of it is called Avionics Group in Thales Alenia Space, Domain Exploration and Science, Italy, that is Turin site. So avionics means a lot of things in our world. Is everything that is electronic, software, guidance, navigation and control, harness, whatever is the intelligent part of a satellite and a model. I was the former head of the robotics and optics and artificial intelligence group that is actually under still under my head. And my relevant experience in this 20 years of work, I'm working since 20 years, was mainly related to surface assets, meaning rovers going to Mars. So I was with increasing role up to system engineer, so manager of the implementation, design, and testing of the ExoMars rover. That is a rover that is gonna go on the Mars surface pretty soon. We are waiting for a lift to get there, but the flight is already prepared. So a few words. So what I'm gonna tell you today is first a bit of overview of what we do in terms of type of satellites or space assets that we create. And of course, I cannot cover everything, so I will be more than happy to answer questions if there is any. We can start. The dissemination can be go very deep, because I know that the domain is not known. So it's more the tips and tricks that is interesting rather than the design that we do. And then I will follow with a discussion, a presentation of the details of the work we did on the ExoMars rover, so you can get the feeling of how a space rover is with respect to a ground rover. both in terms of design and processes that are behind, because you are doing automation, you are doing a lot of cool things. Then to move to the space domain, there is some gap that we have to fill, and what makes this work very appealing. So let's start from the top level. So Thales Alenia Space is a huge company. I hope you see the presentation. So ideally, so what we do, almost everything. So as Thales Alenia Space, Thales is a big company, covers several domains, not only space. Thales Alenia Space covers the space domain in all these fields, from telecom to military satellites to science observation infrastructure. Thales Alenia Space Italia covers pretty much everything as well. In Turin, we are the domain exploration and science Italy. So it's easier to say what we don't do rather than what we do, because we don't do telecommunication satellite and GPS satellite and military satellites. So everything that is low, mid, and Earth orbit. All the remaining parts are done here. So what does it mean? We do space infrastructure, meaning we did most of the International Space Station in terms of thermomechanical parts. So when you see the astronaut from the ISS speaking, or the Orion module a few days ago, well, the thermomechanical part, so the structure around, is done by us. Then we do scientific satellite. What does it mean? Scientific satellite means the one-of-a-kind satellite that are answering to the needs of the scientific community, that are, let's say, that are very inspirational, I must say, because they are the type of satellite, and I will give you some example, spans from seeking for the dark matter to understand really the physics behind who we are, to seek for life on the Mars surface, to measure the gravimetry of Earth, to go close to the sun, and to look at the coronal ejection that disturb our world. So there are many things that we do. It's one of a kind, because usually the needs are very different each other. So it's a very interesting work, especially for if you are going to follow a path toward engineering. It's something that is very interesting for an engineer, because every time we start almost from scratch. So this slide is a bit of overview of the distance that we cover, that is from very close, so low Earth orbit, like the ISS, that is 300 kilometers away from the surface, up to the various orbits that are medium Earth orbit and geostationary, that are in the range of 10,000 kilometers. And then we go beyond, so what it is called deep space. That is quite a demanding environment, because it's not only vacuum, it's not only temperature, but also radiations that are not shielded by our Earth magnetic field. And then beyond, here they are small because they are far, but the Moon and Mars are things that we do. And to give you some example of what we did, okay, these are some numbers, then I will go on something more interesting, but half of the flight that the shuttle did were with our hardware. So we are in this domain since 50 years. So all these modules, when you see this kind of space barrel, as I call them, it's done by us. We are almost monopolist on that. So on the International Space Station, very interesting. So it's almost 300 kilometers on top of us. It goes down and then up through the push of the cargos. So we did many things. We did the most complex parts, to be honest, because all the connection nodes were done by us. So actually, these are the kind of thermostructural element that we produce and we still produce for the space agencies, and also for I heard about someone coming from the touristic part, and we work also for Blue Origin, for Axiom, for companies that are trying to do this kind of things, but for the tourists and not only for the astronaut that are well trained. So we did this connection node. We need one very cool thing that is a cupola, that is the window toward Earth. This is always pointing toward Earth, and it is from where all the images taken by the astronaut are taken. And the main work we are doing now related to the space station are these guys that are the Genius, that are the resupply modules for the space station. So we produce objects that are almost 7 meter long, 4 meter wide diameter, and actually is a resupply. So it's the Amazon Prime for the space station. So we produce, we build it, thermostructural here. We put inside all the things that has to go to the space station, that of course are fuel, is everything that is needed by the crew to survive. So simple water, food, and experiments, because the space station, the main objective of the space station since many years is to do science in absence of gravity. Absence of gravity in zero G. That is, let's say, the main objective of that asset. That module is produced here, is launched before with the Antares, so with the Ukrainian engine from Kourou. Now it's launched through the Falcon, the Elon Musk launcher. It goes automatically in close proximity from the ISS, 8 meter far. Then the robotic arm, the Canadarm, that is this guy here, picks it up and attach it to the space station. There is no automated docking. Then the docking port is opened. All the things are taken by the astronaut and moved inside the space station. All the garbage is pushed inside. Then this module is left, is closed, is left to fall on Earth again, and actually it burns while falling on the ground. So this was it's our main heritage since many years. We started from the aeronautic field. Of course, we were very capable to do the tanks for the airplanes. That is cryogenic. It's complex stuff in terms of pressure and environment. And then we moved to this new domain.
Mr. Merlo, can I ask you how much is that module roughly?
Do you really want? No, okay.
Okay. I think also my students may ask, may wonder how much more or less.
To give you a rough feeling, okay, the module, the recurrent module, is around 80 millions.
Okay.
So it's a big number, yes, but it's not big
numbers
as a scientific satellite, because for a scientific satellite that you start from scratch and it takes almost 8 years from the wishes of the scientist up to the flight, can go up to 300, 400, 500 million. The ExoMars rover, I'm gonna tell you, with its mission, with the lander, with the orbiter, and it's 1 billion. And so we are talking about huge numbers.
For years, does it expire at a certain way? How does it work? So you send it into space, and how many missions can a station host?
Do you mean the space station, right?
Yes.
So usually we have 2 resupply per year. So this is our, in fact, we did the 25, we have contract to 30.
Okay.
The ESS every time is the International Space Station was supposed to be disposed a few years ago, but we have every year an extension of 1. So actually it will stay up to 2032.
Okay.
So we are gonna resupply it to 2032. Of course, there is a problem of obsolescence. So we are working again. We are not we are a private company,
Yes.
but we are actually we work for the institutional market. So we are part of a big infrastructure that has objective. Of course, the objective now are simple objective is to keep alive what we have in low Earth orbit.
Okay.
The objective before the change of mind, the recent change of mind, was to have the same stuff but in cislunar orbit. That was the Deep Space Gateway, so going around Moon and Earth like a unique planet. Now we are steering to the Moon Village. So Artemis is going to focus on making this guy, but on the Moon surface. That of course needs some element.
Anyway,
We don't
they tend to be disposable. They expire at a certain way because of a technology.
They expire because of the technology and also because the elements that there is a certain degree of obsolescence also on the materials, basically rust. Rust is a simple term for Earth on the surface, like the space station is painted white, simple, with a type of dry that is unfortunately suffering the atomic oxygen that is present at that height. And it's going to the yellow, slowly going to the yellow. So after 20, 30, 40 years, even the bridges fall on Earth. So
Thank you so much.
So there is a continuous effort to keep it good, and it is doable. But at one point, the cost of the cost of keeping it alive will be too high to be affordable. So we are gonna change the mind to a new space station. Of course, there is the Chinese space station. We are gonna do the Axiom space station that will be the commercial space station. There was the gateway. We built most of it already. That actually is exposed. And we are doing the module for the surface. That is what I'm gonna show you. Okay, low Earth orbit is what I was saying. Of course, the space station is what we did and what we are doing in terms of resupply. We are doing for private partners space station. Of course, there is Axiom, there is Blue Origin, Sierra Space, so the one that you heard at the television. I will go on the moon. That is actually where the interest is going now. As I told you, what we did, we have mostly thermostructural from Heritage. So we did most of the thermomechanical part of the European service module. So actually, it was the guy on the back of the Orion module made by the Americans that was doing all the guidance, navigation, and control, propulsion, power feeding, and things like that. So the important part of the mission. It was a success. We have other 4 of these that are already under production here in Turin, because of course the path toward flight is very long. So when you see 2028 we are gonna fly this guy, usually the hardware is done now. The gateway that I told you. Of course, we are working also on interesting things on the surface. So still you see our space bar because it's our business. But we put it on wheels. This is gonna be part of the Artemis campaign. So it will be a joint effort from all the countries of the world. It's a world effort actually to populate the moon in phases with astronauts, and this is the type of camper-like solution that we actually already built in prototype here, and that we are progressing in the design of the technology for the moon. Of course, the moon, I will tell you for Mars, but it will be quite similar for the moon. The environment is very hard for ground equipment. We are doing, actually this might be seen as obsolete given the context of the American CLIPS lander, but we are developing the cargo module for the moon surface here in Turin. So we are designing the lander that will be capable to carry around 1.5 tons of hardware on the moon surface. Again, if we are talking about money, as the previous question, the current cost given by the CLIPS provider is around 2 million euros per kilo deployed on the moon surface. That is quite a massive amount of money. So we are working to keep it as low as possible. That means we have to create, like the cargo, like the sinews, the resupply, one element that will be reproduced many times equal, and to keep the mission profile as less costly as possible. Of course, this will be the next, the industrialization, the part related to business. Now it's the engineering challenge. Landing on the moon is not a piece of cake. We are doing a lot of work. Actually, we have the example of the landers that recently landed or fallen on the moon surface. So most of the landers failed during the descent and landing. Why? Because the moon is a complex place. Is a complex because there is the propulsion. So there is a gravity, even if it is lower, it is necessary to have a significant propulsion to decrease the velocity, basically, to land on the surface. It's full of craters that are, since there is no atmosphere, no magnetosphere, there is no protection on the moon surface. So every asteroid falls directly on the surface without any burning due to the atmosphere. So if you look at the moon, simple from any Google images, is really full of craters. So it's almost impossible to find a sweet spot for landing. So there is an inherent risk to land in a crater. So what you have to implement is an intelligence on board to land on the flat surface and avoid craters. But it's complex because there is another story for the moon. The moon is always facing the same face toward Earth. That means that its lunar day takes 330 days, so 1 month. So there are 15 days of day and 15 days of night. So the only interesting part to land on the moon to get some sunlight, constant sunlight, is on the poles, south poles. It is where there is always some sun hitting the top of the ridges of the craters, but of course it's complex because it's the South Pole and the sun is very low. So any image processing that you can dream to seek for the sweet spot for landing has to manage a lot of very long shadows and complex illumination conditions. And this is where, for example, most of the landers failed so far. In any case, this is quite, I'm not gonna deepen more on this. but it's a quite complex and interesting task for almost 80 persons working here, and it's a challenge. So we start almost from scratch on the complexity of modeling the environment, and then we design for this. Of course, there is the infrastructure. We on Earth, we are quite used to have, we move on the surface, we have the GPS. So we have Google Maps, we don't even care to know where to go, we just need an address because we have everything mapped. We have a set of satellites that provides the ground support, so actually the positioning system, that is GPS, Galileo, and other military stuff. We are used to hear GPS because that one is the one that we are using, but there are many other for military and other fields. We are used to get full coverage of communication. Maybe me and also Corrado, we are old enough to remember when there was no mobile phone in our hands. So we had our maps to move around, and there was no coverage on the phone when we were going far on mountain or depressions. Now it's not anymore the case because we have full coverage, we are always connected. But this connection means a ground and a space infrastructure that is enormous. So in the last 30 years, between GPS and communication satellites, we did an enormous amount of work so that now we can really go anywhere and have the communication, internet basically for us, but coverage for phone and positioning system, so GPS. Of course, this is not actual for the moon because for the moon there is no communication system unless you speak directly to Earth. There is no positioning system. Actually, there was an experiment. So from the moon on the face that is facing Earth, it is possible to use the GPS constellation on Earth with some high gain on the electronics. But of course, you are far and it is very scarce, the positioning system, because you don't have the good triangulation. So it's not the way to go. You are the precision is kilometers that you can achieve is kilometer. So what we are doing is both a communication and positioning system for the moon. This is is called the Moonlight project. It is done led by Telespazio, but the satellites are done by us. And actually, we start with a set of 4 satellites that they are gonna go on around the moon surface, and they will fly at some hundred of kilometers over the moon, and they will provide communication relay and positioning system to get the triangulation, so that we will know whenever we will land, we will know where we are, not just by making the triangulation with the stars. That is cool stuff, but you cannot get so precise. But with a real positioning system. So this is another very appealing work that we are currently doing, and it's due for 2030. Mars. On Mars, it was what was very actually, it's a bit démodé, I must say, but it's most of my career. So if you remember or if you heard, there was the Mars exploration rover made by NASA, so the Spirit and the Opportunity, that were the first. There were other assets, but without any scientific meaning. It was just engineering demonstration. From the Mars exploration rover toward the Curiosity that we still hear, toward the Mars 2020 that were all done by NASA. There was some other done by Roscosmos, but all of them they were looking for first the demonstration of the technology, so actually to land and to rove, to move, to drive on the Mars surface, and to characterize the mineralogical environment. But what they discovered was a bit more. So it was not just mineralogy, but it was there was some evidence, even more than what we supposed from satellite images, that water was there and life was there. So what we did actually in the last 15 years is to build a rover with drilling capability to seek for life on Mars. So whenever we will land, that is we will launch in 2028 and we will land in 2030, we are gonna go in the sweet spots to seek for life. And it won't be just it will be really, we are gonna carry the full scientific payload suite to confirm that life existed on Mars, and I will go deep on this. Of course, Mars is an interesting planet. It's a bit far. So actually, what happened is that there was in the last 15 years there was a big effort toward Mars, because the main scientific objective of the scientific community, the planetary scientific community, the space scientific community, was to confirm life outside Earth. That, of course, it's quite an interesting stuff to demonstrate, because it's one of the big questions we have. So if we will be capable to answer in the solar system that life existed also in another planet, then we can almost confirm that we are not alone in this universe. That is, I think, one of the main questions that we shall answer at one point in time, together with other scientific, because we study a lot of physics, but sometimes we rely on assumption that we never validated. Go down. Please, Maria Teresa.
Mr. Merlo, listen, I am a teacher in biotechnology address, and I was wondering if they decided to specialize in biotechnology, could they work in your field?
Yes, actually we are on the engineering side. So industry, usually like us, like Leonardo in Campi Bisenzio, like many other industries, makes the engineering part of the scientific request. The scientific request, together with its ground experiment that demonstrate the thing that works, is usually done by ENAF, for example. So from institutional research center that works on the space domain. So actually, for example, for most of the experiment, like the one I'm going to talk about on ExoMars, the provider of the experiment were industries, because making the scientific stuff ready to fly is an engineering work. But the science that has to do and has to be preserved through this cycle is conceived by someone else. For example, on ExoMars, we had ENAF in Italy, we had IRIA in France, we had MSSA in UK, we had DLR in Germany. We had so the scientific community, usually very linked to the space, to the National Space Agency, are the target to get to work. Then we take the request, and then we are in close relation with the scientists pertaining to the research center to make it real for space.
Okay, thank
so
you.
The simple answer is
about the life. In fact, I thought about bio. So whatever is bio can be. We're looking for something which is a biological specimen and so on. So
then then there is also some opportunity that is small on our side, because we are what is called a large system integrator. That means we do the full satellite, and we are 1,000 person in Turin. So most of the work it's done outside. So we are the one that we do the concept design, we do the requirement, we know who can provide what. We request, we put together, we test in the representative environmental facility, and then we fly. So there are things that competence that we have limited to 5 to 10 person that are working on what is called the SELS, that is the life support system for the astronaut. That is bio, in the sense that we have the circular throw from the vast to the supply of air, water, and food.
Yes.
And this is going beyond for the moon, because on the moon there will be all the part related to the green. So we are going to use the vast for production of food. The food will be going to the astronauts. So it will be, I would say, the real circular and green circle.
Yes, like the model of a green economy, circular, because you reuse, you recycle.
So we have 5 to 10 person that are actually working in this domain. We are not going to produce anything apart proof of concept, because this work, the real work of making the water recirculation system, things like that, will be done outside. But still, the expertise is there, because we have to conceive, we have to know what our subco has to do. So yes, there is opportunity, more on the engineering side than bio, but there are opportunities.
Okay, thanks a lot. And if you see me speaking, it's because I'm commenting to my students, because I'm in front of my classroom. If you see me speak, it's because I'm translating and commenting. And so I am, let's say, cooperating in the presentation in that way.
Oh, thank you very much. I see that you are speaking. In any case, if there is any question, just of me, it's. I know I'm very I'm scratching the surface of the things, because in 1 hour we can spend days on a single mission.
Oh, we know. It's something huge to cover, let's say metaphorically and really. They were, for example, struck by the amount of money which is involved in space exploration. When you mentioned about the price of satellite, but also when you mentioned about the prices to cover Mars exploration and so on, they were really surprised, because probably they didn't know, or they never imagined how much money has to be put into, in addition to the effort, to the knowledge, but money. And so we know that it is a huge business also.
It's a bit, again, it's the launch, the most recent economical change in our world was SpaceX with Elon Musk. So what happened is that before they were the launch capability, so the rocket capable to lift off stuff from Earth to space, that are actually bombs, because there are a lot of fuel inside. They were very, very costly. There were only American, Russian, and few European providers. So Ariane in Europe, there was NASA directly through Lockheed Martin and NG in US, and the rocket from Roscosmos. Now, but of course, there was more and more need, because the satellites are not just science. There are telecom, there are constellation, there are
many fields involved.
What happened is that there was an interesting market from a private businessman, that was Elon Musk. So he developed the technology to cost few. Let's say to lower the cost of launching stuff. But to give you the feeling, if you wanted to buy a Falcon launcher, a lift to space, a full Falcon launcher to land something on the moon surface is 100 million. So even if it is, you see that there are many that are flying. If it is alone, if instead you buy the service, because if you ever saw, there is the launcher, then there is a fairing, that is a nut that opens, and then there are many satellites inside. So it's a service. If there are 100 satellites, you split the price for 100, and you lower. But still, it is a very costly thing. As all the things that are not massive production, they are very costly, because that is the design. You pay for designing it, and not just for the materials for producing it. This is the simple reason for that. On the science,
we're also surprised because we never realized that satellites are providing their GPS, their internet, their everything. We never realized
no,
it.
if you there is I don't have a slide for that, but actually there is one thing that is very actual and interesting for everybody is the space debris. Why? Because there are so many satellites in low Earth orbit, so in hundreds of kilometers on top of us, that there is a higher risk to collide with something else. This gives the flavor of and there is an image where you see all the satellite, a dynamic image, and you see all.
We saw it. We were said that there are. Is it true? 7,000 satellites, and so they need to calculate exactly beforehand the path to avoid.
Exactly. It's exactly like that, because previously there was no rule to have an automatic disposal of the satellite. So disposal was the satellite was set to get there, and then to slowly fall from the Earth orbit to Earth. And this might, if it is at a certain height, even uncontrolled, might take tens of ages, tens of years to fall down, and it remains as a debris for that time. So now the rules are that there must be sufficient propellant to move to graveyard, that means go away or go down, so that it does not remain as a debris. But of course, what is there is there. So there are services that are requested everywhere. We are doing one of those. That is space debris capture and bring to fall on Earth. But of course, it's not efficient with these numbers. So the best case is to design so that in a green way, so that they dispose automatically at the end of life, and launch now with some degree of control at the beginning.
Yes, because when we saw the picture, it looked like a highway full of satellites, like cars.
But again, one thing that sometimes I never mention, but now that we get there, it might be interesting. One of the disciplines that we cover in designing a satellite is what is called MMOD, that is the micrometeoroids protection. What does it mean? It means that around Earth, because of the debris, so from collisions, or because of small piece of asteroids or whatever that remains there, there is a significant risk to be hit by a particle of few millimeters that goes a very high speed. And you might have seen there is this door of 3 centimeters of aluminium with an hole inside for a rice grain that is moving at that speed. And this is the physics. So if the mass is low but the speed is very high, the the force is high. So very simple, very simple. It's physics. So you study physics, but then it applies.
In fact, one of my students said, I asked him, would you like to work in this field? And he said, there is too much physics, so it's not my field.
It is because, again, we do scientific satellite. So our work is to make, of course, the satellite that carries the scientific instrument. But the way the instrument has to be, the satellite has to be designed to achieve the science cannot be done by engineers alone. So, for example, for every of those satellites that you see here,
Yes.
we have persons inside in our performance and modeling group that comes from astrophysics and physics, because they have to build what is called a performance model that takes the scientific meaning, so it models the scientific instrument, and it merges with the capability of the engineering platform that, again, with a high range of temperatures, like the pointing toward the measure toward a very far constellation is made by how precise you can stay in that position. And it is not just a spectrometer. It is not just we have to go to do a good spectrometer. We have to do a good spectrometer that complies with the capability of keeping the pointing. At the same time, we have to. So we have this kind of meta figures that are in between the science and the engineering that creates the glue that is necessary. Again, here you see we mount the science that we do is really on every possible domain of science, because there is from infrared to gamma ray to X-ray to measurement of gravitational field to imaging in all the possible field of view, mapping of Earth gravity. So there are every time there is something different that we mount.
Okay.
And of course,
excuse me, I'm moving to the library, so I'm disconnecting this meeting, and you will find me in the connection with the library. Okay.
Okay, no problem.
Okay.
Shall I wait you, or can I go ahead?
No, you can go on. Thank you.
Okay. So these are examples of satellite we did, and it gives the feeling of the one of a kind, so unique type of satellite we do, because some of them are remains close to Earth, so they are low Earth orbit or geostationary. Some of them are going to Mercury, so they are actually going toward Mercury. Some of them are in what they are called the Lagrangian point. You will study them. That are places where there is all the gravity of the planets keep you more or less in a position without having too much to struggle to remain there. There are things that are placed on the moon orbit and Mars orbit. So everyone has its own design. The type of sensor, actuators, propulsion, thrusters that you use are different. So every satellite is different. You see, even from the shape, they are not. They don't look the same. Example, if I manage. This was Euclid. Maybe you have seen this image from recent from RAI last year. So it's a telescope to stay on the easy side, that is capable to take very important images from the scientific perspective. So we are mapping the dark universe. You know, if you are gonna go on physics till the end, you will discover that many things are based on assumptions, and those assumptions have still to be validated. And the scientific community on Earth and in space are going toward that direction. Other example on Envision, it's an orbiter around Venus, so it's a difficult environment. I'm not gonna speak about Venus as a planet and surface because it's unmanageable for everything. Very high pressure, very incredible temperature, so it's too complex to be managed and not interesting at all, because there is nothing you can get there with with that environment. If you are curious, just look at Venus surface, Venus environment, and you will get a very bad feeling of that place. Of course, gravitational waves, that is a big scientific questions for the origin, for the Big Bang, for the origin of the universe that we have to answer, and this is going to be done with 3 instrument suites mounted on 3 satellites that keeps this triangular formation million of kilometers far away each other. So very complex. It's very something that nobody did before. Telescopes of any kind. Of course, when you see the everything that is related to gravitation, to the gravity on Earth, so the very precise measure of the geoid, the Earth geoid is done via GOCE. That is a satellite that we did. Other examples. Okay, this was in orbit services. Okay, let's go on something a bit more. Let me go on ExoMars, because this might be of high interest, because we are gonna go a bit more on the hardware that is easier to be. So now I'm gonna focus on one of the thing that I told you, that is the rover that we built here in Turin, and we tested it spread all over the world, and is ready here, and we are gonna launch it in 2028. So this guy is a vehicle for Mars. The name of the program, and this gives the flavor of the time necessary to build these very complex things, that of course time is linked to cost. So Mars is unknown for us, so we never got there. So whenever you try to build something for Mars, you have to create everything from scratch. Not only the hardware that will fly, but also your knowledge. You have to build the knowledge and the models of what is Mars: temperature, density, type of terrain, based on scientific observation. So what the ExoMars program, the main objective of the ExoMars program, you see dates that are superseded actually by events, is an enormous program where there was a first mission that we did in 2016, so 10 years ago, that created and deployed an orbiter, so a satellite that is currently rotating around the Mars surface and is acting as a relay, so communication relay, so it gives communication to the surface assets, and a demonstrator of a descent module, so one lander for Mars. The other important part that actually changed a bit shape is the mission with the rover. So the second mission, the one that is still on Earth, because we were ready, but we were relying on some element from Roscosmos, and due to the Russian-Ukrainian war, we had to stop the collaboration with them. We are creating the lander, so we are taking some time to, just a second. we are rebuilding part of the lander to land the rover on the surface. So it's a complex mission because there is everything. There is from the launcher to the carrier, so the satellite that brings from Earth to Mars. There is a lander capable to go down to the Mars surface and a rover. Let me. You see here, this was well. Actually, unfortunately, it's difficult to make filming in space, so we have to rely on simulations that are done based on the real telemetry. But this was the first mission that we did in 2016. So you see that the interesting thing is the staging of the launcher. In this case, we launched through a Proton. Where are you? Sorry, I lost a bit. You see that the launcher was a Proton launcher that is made in stages. So every stage actually is a fuel tank to make it simple. With thrust support, of course, the main propulsion is necessary at the beginning to leave the Earth because the Earth gravity is quite strong. While to move on the deep space, actually you retain your speed and you have also only to accelerate and decelerate, so the thrust are smaller. So the launcher brought us in the right direction out of Earth, and then the carrier, that is this guy, drove toward Mars. Of course, it is not a straight drive. To keep the propulsion budget, so basically the amount of hydrazine, of fuel that is used below, you use the gravity of Earth and Moon to get to Mars without spending too much energy. That is pretty much what also Orion did to step back from the Moon to Earth, to use the Moon gravity to accelerate toward Earth. Then there was the carrier and then the demonstrator of the lander. For the second mission, that in this case is a bit obsolete because the launcher is going to be the Falcon X instead of the Proton. In fact, the first part of the movie is cutted. You see that it's pretty much the same with respect to the first mission. So there is a carrier module that in 7 to 9 months, well, actually it was 7 in 2022, now it's going to be 9 in 2020 months, we reach the Mars surface. The lander is left close to the Mars orbit. Then actually the lander, you see, since Mars has a thin atmosphere, it is possible to decelerate using the atmosphere. So actually there is an heat shield to slow down a bit the speed, and then the landing is done first with a parachute and second with propulsion. So you see that the last part of the landing is done with actually a microsatellite that with thruster that are engine that are actually moving to the surface, and from that point the rover goes out. Of course, this is a rendering. You are going to see the real stuff in few slides. So what is the meaning? Okay, and I don't want to teach you how to do a Mars rover, but to give you a feeling of what does it mean to work in space and to design something for Mars. So Mars is an ugly place, so it's very complex. We go there, why? Not because we like Mars, because we think the scientific community thinks that there was life and maybe there is still life underground. So you see on the bottom left, Mars, of course, on the top side, on the top surface, even if there is some atmosphere, there is no magnetosphere. That means that the cosmic rays and all the radiation environment is not shielded by the planet itself. So everything is sterilized. Sterilized means it's like on the medical, when you get to surgery. So everything is sterilized for 1 meter of depth in the terrain. So if there is any life, in few years, it is completely destroyed by the radiation that are hitting the Mars surface. So to have a possibility to get to amino acid or any biological trace of life, you have to go down under at least 1 meter. In that case, if you go down to 1 meter, you might see still something that is preserved, like the fossils. So why we are going there? There are many interesting papers and even documentary from the Mars rovers and observation, because for sure there was water on Mars. And even if you go on Google Mars and you look at the map and you go very close, you really see the delta of the rivers. So there was, for sure, there was water. Not sure there was life, but the type of minerals that were spotted via images and via mineralogical instrument gives a high degree of confidence that life existed there, because there was some product that only life can do. So what we did was to choose, together with the scientific community, it was not an engineering decision, it was a merge of the two things, to seek for one of the best places to spot life. Where is the best place to spot life buried on the terrain? Is on close to the river, or in this case, Oxyplanum, a delta fan of a river on an ocean. So actually what happened, there was deposit of the clays, argille for the Italians. So actually what you see, tufo, is called in Italian. So the type of terrain that is hosting the fossils, that was then covered by sand, so that they were not sterilized. Of course, there was a bit of abrasion in the years, because there is some wind, something on the moon, on the Mars surface, that creates a little bit of erosion. So Oxyplanum is the best place where to get clays buried in this configuration. So this is why we get there. But of course, we have also to pick the right place and take a sample of the terrain at the depth, and then, of course, we cannot return the sample to Earth because it is too complex and costly. So we have to bring together with the rover, we had to create the scientific suite made by infrared camera spectrometer, gas chromatographer, and life marker chip that are capable to get the amino acid that are the trace of life. So this is actually what we did, and it was quite complex. So here you see again is a rendering, but of course there was an objective, and we had to choose where to go and the type of rover toward the objective. So the objective was not to travel on Mars. The objective is to seek for life on Mars. Which are the constraints? Many constraints. First, okay, these are the key facts that are also constraints at the same time, but the constraints are in the next slide. The trip to Mars is 8 months. In this trip, 8 months, you have to survive. The rover has to survive. That is pretty complex, because there is quite an aggressive radiation environment. There is temperatures, because without the atmosphere that shield when the sun hits in deep space, your temperature rises to 150 degrees, and when it goes in dark, you slowly goes toward the 0 Kelvin, a bit more, but you go down to 200 degrees Celsius. So you have to design it, keeping in account that you have always to warm up when it is cold and to reject it when the sun hits the rover. The mission, Mars has seasons. So even if there is no water circle, meaning there are no NAMs, there is no rain, there is no hot water actually, there is dust suspended. There is a sort of fog on Mars that, depending on the season, is higher and lower. There is you might have heard, there are dust thunderstorms, dust storms, they are called dust devils and dust storms on Mars. And when it happens, then you don't see the sun. So it's like when it is very cloudy on Earth. I want to give you an idea of not how hard, but how interesting is making an object that has to work on the Mars surface. First, energy. So we are used to patrol. This is the basis of our life. So we don't even think how energy is precious on Earth. We start now because of the shortcut due to the geopolitical constraints. But on Mars, without radioisotope source, you have to rely only on the sun. That means solar panels and batteries to survive the night. So the efficiency of a solar panel is 30%, nearly, a bit less, of the energy that hits the planet. Mars is a bit farther from Earth to the sun. So the amount of energy you can generate is very low. I will go on it, but it's like 1 kilowatt hour per day. Kilowatt hour, it's very, you cannot even charge the phone with the energy. You can keep an air dryer on for less than 1 hour with the energy we generate with the Mars rover. There is quite a harsh environment in terms of temperature. So these are plots of temperature, but to give you the flavor, during night on Mars, the temperature goes down to nearly minus 100 degrees Celsius. That is far beyond every capability of the electronics we have in our hands. So if you look at your phone, try to put it at minus 20 degrees, it stops working. The military stuff goes down to minus 55 degrees Celsius. If you go down, it stops working. So the type of things that you have to do on the electronics because of those temperatures are incredible. The soldering, the way you design it. Of course, there is a shortcut that is keeping the object warm. That means spending energy, the few energy you have, to keep the electronic at the right operational temperature. That is minus 40 degrees if you use a military device. In any case, if you put your iPhone on Mars, it won't work after a few minutes. There is no problem on the hot side on Mars. That is actually the case for the Moon, because on Mars there is a bit of atmosphere that keeps the temperature. There is a thermal inertia that lower the bound, not like on Earth, but lower a little bit. So the temperature goes to close to 0 degrees Celsius. It's never hot on the Mars surface. Then one other thing that is challenging for Mars is the very scarce communication capability. So if you want to communicate directly to Earth, so you have your cool antenna that has to speak directly with an antenna on Earth, you have to spend a massive amount of energy that you don't have because of the strong energy limitation. So the only thing that you can do is to rely on an orbiter that has a wider solar panel. You send to it the rover send to it the rover telemetry, and then the telemetry is relayed to Earth. This means that you cannot drive with the joystick the rover from Earth. You have to equip it with some degree of intelligence. That since you are going to pay for it, the institutional market is going to pay hundreds of millions. Of course, you have to be very sure that it works. There is another thing that we are not used again on Earth, unless only on the nuclear power plants, is the radiation. On the Mars surface, since there is no magnetosphere, there is quite a massive amount of protons, heavy ions that are hitting the surface. So what does it mean? That we hear about gigahertz on the processor, the mobile phone that are going smaller. That means how this is done is to work on the PN junction, so on the electronic itself, so that very few electrons moves from one place to the other to say 0, 1. In an environment where you get protons every few minutes, of course, this won't work. So the technology you have to use is bigger. So actually, a space computer is bigger because you have to be sure that the radiation environment does not destroy your 0, 1 in the memory, but also shielded. Shielded means you have to cover it through aluminium or any kind of Kapton. There are many things that are protecting the electronics. Of course, there is the problem also that of the heat rejection, because here on Earth, if you open your computer, there are fans beside your processor, because it works fast, high frequency, it consumes power, very concentrated in the place, and if there is a lot of power, you have also to dissipate. There are dissipators and fans to propagate. There is few atmosphere. So the fan is not efficient on Mars and not efficient at all on the Moon, that there is no atmosphere. So the heat rejection, the way you pick the heat and you move outside, is a complex thing for space. So you cannot have concentrated heat and dissipation of energy. Again, you destroy the basis of the ground electronics when you get to those constraints. This is, again, it's the cool part of doing space, to reinvent actually the wheel. Actually, we reinvented the wheel, you will see. Other important thing, I told you already, there is no GPS. So actually you land, actually you can have the triangulation when it lands, and then you have to move like that. So you cannot geo-reference unless you find a clever way through the communication and look into the horizon to understand where you are on the surface. And trust me, is a complex task. There is one last thing that is very important, that is very constrained in design. In this case, we were looking for life. We are going to look for life. So everything of the flight rover has been assembled and is kept completely sterile. What does it mean? That nobody never touched with his hand this rover. Nobody ever breathed close to the rover without a mask. So the way we assembled it is through glove box. These are actually the same as how is it called? The lethal virus
management, you know, the biohazard glove box, this one. So we assembled a rover in this like that. We are keeping it over-pressurized. So all the internal part is kept over-pressurized to avoid that even the air that is polluted, even in a clean room, goes inside. So there is an enormous complexity even in the transportation of something that has to remain completely sterile. And of course, before building it in the production, you can sterilize the things just because you can cook them in the oven for the mechanical part. While for the electronic part, you have to use IPA, that is alcohol isopropylico, so that you really clean without putting water. But again, the process behind building something that has to remain sterile from the beginning to the Mars surface, including putting it maybe on a boat to move on the other side of the ocean to be shipped on a rocket, it's complex and costly. I have few minutes, so I'm gonna show you a bit another couple of things that is quite interesting. Of course, when you have to build a satellite, or in this case, a rover for the Mars surface, you have to prove first to yourself and then to your customer that this thing will work on Mars. And it is complex because we are on Earth. We have a different gravity. On Mars, it is 1/3. There is an atmosphere, while on Mars there is a very thin atmosphere. There is a different temperature. There is a completely different radiation environment. So what in the development of this, of a space assets, almost 1 year of time is spent to create an engineering, what is called a qualification model, that is a replica of the flight model, that is tested in representative environment. What does it mean? That there are enormous barrels that are called thermal vacuum facilities, where you can put your space hardware, you pull out the air. In this case, you pull out the air, you put a bit of carbon dioxide to get to the Mars environment. You have, they are called shroud, but you have the possibility to control the temperature of the inner part of the chamber. So actually there is nitrogen to cool it down, and heaters, so electrical resistance to warm it up. And you create Mars on that environment, at least from a thermal and vacuum perspective. And you do your part of the mission that you can manage in that small barrel. Then there is the mechanical testing. So the launcher itself is not an easy environment. Why? Because it's very noisy. So there is an acoustic environment. And trust me, when the noise is very high, the balls screw down and falls down. So it's complex. You get a vibration. So actually, when the rocket starts to move, it's like a very high frequency vibration. And every mechanical part that is left open, like that, it breaks. And if you don't put, we call head locking. So actually, if you don't put the bolts before doing these things, the bolt actually, they screw back and they fall. It's incredible. So we have the mechanical facility, and we spend time on the mechanical facility to create the environment, the launch environment, and the dash and landing environment to be sure that it will work. There is what is called the electromagnetic compatibility. So everything that is noise from the electromagnetic perspective has to be characterized there. So we do all the testing to prove that this guy works. Of course, part of the testing is functional. So we have to prove that in Earth gravity, this guy will work. And it is actually what we did. You see here a bit of benches, but let me spend the last few minutes to show you a bit what we did. Of course, the flight guy is in its tent, over-pressurized to don't get polluted with our biological stuff, but we have the replica. This is the complete replica, is the flight, the same guy, but that we use on Earth. So this is the ground replica, the Earth twin, I call it now. The digital twin takes use, and you see. To get the creation of the Mars environment, we created a gravity compensation system. So this system, that is the rover, the ROD, rover offloading device, pulls up the rover, removing 2/3 of the weight, while the rover is capable to move in Mars representative environment. You see that the way you design the thing for space, considering the constraints that I told you, brings to solutions that are completely different from what we are used to see on ground in automotive field. Here, the objective was we have to spend as less energy as possible and negotiate high slope because we have to go on the juicy spot for the science. So what we did is a locomotion system with the suspension is done by the wheel itself. So there are springs inside. The traction is done through electric motors on the hub of the wheel. The secondary suspension actually are boogies, so passive stuff that basculate on the surface. So it's completely different from a new body that you would have expected on ground. But this is the output of the trade-off, taking account the constraints: low mass, low energy, and so we had to redesign the wheel. Sorry for the noise. There is another interesting thing. You see that there is also the complexity of just a second, sorry. Prego. Sono in call, scusa. Grazie mille. Okay. Scusate. Sorry. You see that one of the problem the American rover had was to get buried on the subsoil. So actually what we did is a way to escape from that condition. That is actually to move a little bit the wheel while propagating a bit the working device. Of course, autonomous navigation. This is what is more closer to our ground reality. So the capability to map the environment, to go around. But again, if you go on ground in a research center, the focus is given to guidance, navigation, control, and the AI to drive in the proper way, the Google car. In our environment, this was peanuts with respect to the design process to get to this flight equipment. So it goes, the space domain goes directly on the core of the design. So materials, electronics, simple software, very reliable. So we start really from we need the competence to make the stuff, to understand the environment. We need physics, we need astrophysics, we need everything. It's not just engineering. Again, this was an example of navigation. Of course, we had to test, and that was quite interesting, a scientific, meaningful path, burying things target to be demonstrated that the instrument set is capable to spot the juicy spot for making the drill. We did actually test the drilling. You see, this is the drill. This is a tube that we fill with the right type of material, and we make a hole down to 1.5 meters. To give you a feeling, the drill is consuming less than 60 watt, 60. So your drill at home that you suffer because you cannot make the hole is 2 kilowatt. So it's a 2 order of magnitude, almost 2 order of magnitude. So the efficiency of the type, if there is an optimization to get to local consumption to make this kind of activity. The locomotion system is low and then 50 watt in other conditions. Keep power consumption very low. And that means streamline as much as possible the thing. That means we cannot reduce, we have to do from scratch low the physics of the things. And then, of course, the other very important thing that we did is to prove that we can seek for life. So we did a full test campaign to show that from the sample to the instrument execution to get the amino acids, everything was working. And it was not an easy take because the sample has to be processed in the proper way. So it has to be milled, destroyed, milled, and there are things to do that. Distributed, closed, warmed up to 1000 degrees to go to a cross-gas chromatographer. And it is actually what we demonstrated on Earth and we are going to put on space. Okay, just to give you the feeling, those guys are there. Those are the flight equipment and they are ready to fly to Mars. That's it. I think that was the time available. Sorry for jumping here and there. It's difficult to focus on something, but I hope you enjoyed this speech, this seminar. So thank you for listening to me. Maria Teresa, can you still, Corrado, can you still hear me? I think you are muted.
Okay, yes. Vai, Rusconi. Can I speak? Okay. Yes, we can hear and we can see. We have 4 minutes left, okay?
Okay, no, I'm just saying I think we can stop here.
Okay.
There is no other. That was the slide for the question. So sorry for having jumped here and there, but
no, that was
was
impressive.
Really,
no, that was impressive. We loved it. We have a great enthusiasm in your activities and in the presentation that you have just delivered. So we really enjoyed it.
So I hope it was inspirational for the young guys. Because it's important to give a direction on the study.
Can you hear me?
You can go in Italian if you feel more confident. No worries.
How much does it cost you to build one of the various SVT types?
SPT, what does it mean? Cosa sono gli SPT?
Yes.
We are interested in money today, more than in science.
No, SPT, what does it mean?
What do you mean? You mean the hardware? No? The first one? No? Okay, no, the technology you were showing and the one tested at your Turin headquarters, where your hub.
To give you a feeling, the ExoMars rover, the contract we got from the European Space Agency, overall the full mission, the one with the previous launch, everything is nearly 1 billion. The rover itself is a contract of around 300 million euros. This is
Okay.
the, of course, it took ages, and there are many elements, and it covers also the launcher, and the cruise, all the elements. So if you pack together, there are many satellites together.
And in terms of time, how long does it take to build it and also to test it?
So usually, from the idea to there are two aspects. The real time to make the work, that is around 5 years.
Yes, okay.
Then the way you not negotiate, but you get the funding because it's institutional money. Every
Yes.
2 to 3 years, there is a ministerial where they decide what to fund and give how much money. So usually, because of the money constraints, you dilute the execution time, the creation time to something close to 8 to 9 years.
Okay,
This
so a
is for
long
a scientific
time.
satellite. Of course, if you ask me, the supply of the space station, it's 1 year from the purchase to the flight, because it's a recurrent stuff. So we build it as the previous one. So we go straight.
And during the test, for example, do you hire other resources, human resources, or do you supply for the human resources in your company?
We actually have a team of around 1,000 persons that are moving from one project to the other. So we don't have temporary employees or very limited temporary employees. We have our assembly, integration, and test department that hires people, and we actually make use of them, or they are actually working on satellites. Usually the environmental test campaign, the launch campaign lasts from 9 months to 1 year.
Yes.
And mostly it is abroad, because the facilities for making the test are sparse in Europe.
Okay, not only in Turin.
Not only in Turin, there are many. So it happens that we go personally. I was in Toulouse and Cannes to make the environmental
so that was in
test
France.
facility.
Okay. Yeah. And we were wondering, Corrado and I, would it be possible next year to visit your company, to visit, I don't know which part, which is visible, and is it feasible to come with some students?
Yes, of course. We have to organize some week in advance because of the authorization and some paperwork, but we are used to host visits without any problem. Can be 2-3 hours, and we do the trip to show all the thing. It would be very interesting for everybody. So it is the kind of dissemination that we like to do, because we convince people to remain in this domain.
You are right. In fact, we were convinced, so it worked. You nailed it, as they say. Sorry, we really wanted to thank you so much. We enjoyed it. It was, yes, tell me. Okay. Derek, have you a question? First of all, hi, Derek, because I first greeted Miss Manson, but you switched. Because we read Miss Manson, but we have Derek.
Yeah, I've only just came in. Sorry.
No problem. Thanks for joining us, okay, Derek?
Oh, thanks.
And
just
also,
to say, the pupils really enjoyed that. I've just had to send in away there, but they were really enjoying that there.
Okay. Okay, thank you. And also, Amada, thank you for joining us. Corrado got in touch with you because you couldn't connect. Thanks a lot for joining us. And Mr. Merlo, a huge thanks on behalf of my students, my colleague Corrado. We really enjoyed your presentation, your dissemination, and next school term, we hope we can also join you at your premises in Turin. And congratulations on your work, which is really impressive. Yes, interesting,
Thank you very
appealing.
much.
So thanks a lot, and it was really inspiring, even to me, that I'm not a science person, because I am a teacher of English, so I am into literature, into poems and so on, but I really loved it, because it broadened my mind, and it opened a new world. So thanks a lot.
You know, it's always difficult because I'm an engineer. It's difficult to be inspirational as an engineer. So
No,
I've
you
tried
are,
to
you
do my
are.
best, but I know that it's not my business.
No,
So thank you
were.
for hearing me, and thank you.
And you were also very communicative, and you made everything very easy and understandable to our students, so they can get into the subject easily. So thanks a lot, and talk to you soon. Enjoy your day. Bye bye, Derek.
Ciao.
Bye bye,
Grazie.
Ahmad. Bye bye. Thank you so much.
Bye bye.
Bye. See you later.
Hai chiuso?